Hello, good morning. Am I audible?
Yes, sir.
Huh? Good morning and welcome to our lecture on advanced power electronics. Last time we have just discussed the classification of inverters. One is based on the type of voltage source, DC voltage source, and two types of DC voltage sources. One is a DC voltage source and another. So here DC voltage source, the output voltage polarity magnitude of output voltage remains approximately constant here, and that is we can call as a voltage source, DC voltage source. And we have seen the examples for this DC voltage source. Then inherent DC current source is not available, so we have to convert the voltage source into a current source. One is you have to use a large inductance in series with voltage source to make it current source. Other is we can use a controlled voltage source. In a closed loop, we can make it as a controlled current source. So two types of inverters, voltage source inverter and the current source inverter, and we have discussed these. In case of voltage source inverter, very important is that this DC voltage polarity remains constant, whereas the direction of current can be bidirectional. So this particular inverter always works in the two quadrant. Depending upon IDC and VDC, if you plot it, our IDC can be a positive or negative. So and VDC will be a positive, and based on that, so let us assume that this axis is our VDC, x-axis is VDC, and y-axis is IDC. And then we have seen that this particular inverter, IDC can be a positive or negative. So this will be always the two quadrant operation of the particular voltage source inverter. Power flow is bidirectional. Then in case of current source, we have seen that we can't change the direction of IDC. IDC will remain same, but the DC voltage appearing at input of the inverter can be a positive or negative. And again, this CSI will be also having a two quadrant operation. And now we have seen that in case of number of phases, we are having a single phase uh, inverter in under the voltage source inverter. We are a single phase inverter, and in that we are having a half bridge and the full bridge inverter. Whereas three phase bridge inverter, we are having 120 degrees mode of conduction, 180 degrees mode of conduction, and PWM switching. We are having a various PWM switching. So our trace is on a three phase, so we can directly go towards a three phase voltage source bridge inverter, VSI bridge inverter. And if you see it here, uh, we are having a three legs. So this we can call as a three legs. So it has having a three legs. Totally we are having a six devices, and we have seen that these devices are here. We have shown the devices are IGBT with anti-parallel diode. Another option is we can use the MOSFET. So these two, and very big application we can use the GTO. But in case of particularly inverters, we never use the thyristors, and the reason we have discussed yesterday. So why we can't use the thyristor particularly for inverter application? Anybody can explain why we can't use the thyristors for inverter application? Am I audible?
Yes, sir.
So why we can't use thyristor? What are the reasons? The first reason is thyristor is a semi-controlled device, and for turning it off, we require one circuit, and name of that circuit is a commutation circuit. So we require two circuits. One will be for turning on the thyristor, that we can call as a turn on circuit or the firing circuit, and a circuit used to turn off the thyristor. What is name of that circuit used to turn off the thyristor? What is name of circuit used to turn off the thyristor. The name of this circuit is the commutation circuit. So we require one separate circuit for turning on. We require one separate circuit for a commutation. But commutation circuit is bulky. It has carry the load current, and it is having L and C components, and that's why the commutation circuit is bulky. Whereas thyristor is also operating switching frequency is low. Whereas these drawbacks can be eliminated in case of IGBT or MOSFET. We are having only one circuit. With the help of that, we can turn on by giving a positive voltage between gate and source. Similarly, for turning off, we can get a zero or negative voltage. So we require a simple drive circuit. Control circuit is simple. Turn on and turn off is very easy, and these devices will be operated at high switching frequency. That's why for inverter we are using the IGBT or the MOSFET, and we are using the 6 devices, and names of these devices are given as per the conducting sequence. So we are having one leg, we are having 2 devices, that is S1 and S4. A second leg devices are S3 and S6. And third leg devices are S5 and S2. And from each leg we are taking the output. So ABC, that will be, we are connected a 3-phase load, and we are having the voltage source. Now we can control the output voltage and frequency. Whereas operating modes of these, initially we can go for 180 degrees mode. Quickly, we are already covered this. So we are calling it as a 180 degrees mode of conduction. Another, it is also called as a square wave mode of operation. So we are in 2 modes, either 180 degrees mode of conduction, and another name is a square wave inverter mode or the 6-step inverter. And now here we have seen that we are having the 6 devices what we are having, and this we are shown the switching signal. So here logical 1 means the device is on, logical 0 means device is off, and you see it here. So this is our particular half duration 180 degrees. Each device is on for a period of 180 degrees. So our S1 is on for 180 degrees, then off for 180 degrees. So this is the S1 device, and in the same leg we have seen that both devices should not be on simultaneously. S1 and S4 should not be on, otherwise a DC supply, a voltage source DC supply will be short circuited. And to avoid that, so here S1 is on for 180 degrees. When S1 is off, you see the S4, when S1 on, S4 is off, and when S1 off, S4 is on. So this is the case for a first leg. Second leg, we are having devices S3 and S6. But we have seen that a phase shift between S1 and S3, phase shift between S1 and S3 is a 120 degrees. So this is the phase shift between these 120 degrees. So this is our phase shift. We are having a 120 degrees between S1 and S3. And again, S3 conducts for a period of 180 degrees. When S3 is on, S6 is off, and when S3 is on, S6 is off, and when S3 is off, S6 will be on. Now third leg our devices is S5 and S2. So S5, we have seen that it will have a phase shift of 120 degrees from S3. So this is a phase shift of 120 degrees from S3. And again, we have seen that when S5 is on, S2 will be off, and when S2 is on, S5 will be off. So we have drawn the switching signals particularly, and this is, we have shown it here, a 1 cycle time. Here, what if you see it here, this will be our 1 cycle time TP rate. And in case of this TP rate, okay, we have shown it here as 60 degrees divisions, and we have shown that we have shown the devices, conducting devices here, and we have seen that. So here first 60 degrees our devices conducting are 5, then 6 and 1. If you see it here, similarly we have shown it here, next 60 degrees 6, 1, 2, then 1, 2, 3, 2, 3, 4, 3, 4, 5, and 4, 5, 6 and all. So each device is conducting for a period of 180. But how many devices simultaneously conducting? The 3 devices are simultaneously conducting one device from each leg. So this is the switching signal. Then we want to go for, so whatever we have discussed here, we have summarized here. So you can just whatever we just discussed, that each device conduction period is 180 degrees. Each one device from each leg is on. Three devices are on simultaneously. Devices are named as per conducting sequence. And here, when S1 turns off and S4 turns on, during that time, both devices should not be on simultaneously, both devices, otherwise dead short circuit will, and there is a dead time is required to avoid the short circuit of DC link. And phase shift between the links is legs, between this leg and this leg phase shift is 120 degrees. Similarly, second leg and third leg phase shift is 120. Similarly, third leg and first leg phase shift is of 120 degrees. Now we want to find out the output voltage of 180 degrees mode of conduction. How to find out the output voltage for 180 degrees mode of conduction? And now here, let us assume that we are considering only A and B. So here we are considering the devices of phase voltage VAB or line voltage VAB. We are interested in finding out the line voltage VAB and which four devices are taking part in that. So in that case, particularly four devices, we are going for VAB. Our VAB is the line voltage. VAB is the line voltage. And how to find out the line voltage? And for that, particularly VAB, we are having the six devices. When AB is positive, A is positive with respect to B when S1 and S6 are on. So here we are showing particularly when S1 and S6 are on. This is S1, what we are having devices, S1 and this S6, S1 and this S6, S1 and S6 are on, then our output voltage is VAB is a plus VDC. Similarly, when S3 and S4 are on, so B is connected to positive, so it will be minus VDC. And now let us consider upper two devices are on. Let us assume that S3, S1 and S3, these two devices are on. Then we have shown that particularly this our load terminals will be shorted. So here when these two are on, B is connected through this to the A. And so whenever S1 and S3 are on, so load voltage is a zero, output voltage zero. So this is a, you can call it a truth table, particularly when VAB is positive, that will be S1 and S6 are on. VAB is plus VDC, S3 and S4 is on. Output VAB is minus VDC. Here upper two S1 and S3 are on, or S4 and S6, these two are on, then our output voltage will be a zero. Similar, we can find out the second voltage VBC and the VCA. Okay, you can just legs will change and our logic will be the same, and we find out that what should be the. So here we are getting our output voltage, line voltage. We are having three values, either plus VDC, minus VDC, or zero. If you use this truth table and you just go for this which devices are out, based on that we can find out the line voltage waveform. So here our line voltage waveform, this is a plus VDC. Okay, I am showing it here. We are not going in detail time for this. So we are having here whenever VAB, so which two devices will be on here? S1 and S6 will be on. For VAB is the positive. Here we are getting a zero voltage 60 degrees. In that case, S1, S3 or S4, S6 will be on. And here negative one voltage of minus VDC, it will be S3 and S4 are on. So this is our line voltage waveform VAB. And this waveform we can call as a quasi square wave output voltage. Similarly for VBC and the VCA. So phase shift between VAB and VBC is 120 degrees. Similarly, VBCA and VCA is a 120 degrees. So here, if you just change the switching signal of two legs, so whatever second leg switching signals I am giving to a third leg, and third leg switching signals I am giving to the second leg. So what effect will take place? So here we are having a six switching signals. We are given this. Just we interchange two legs of signals. A middle leg I am going to a second leg signal I am giving to the third leg, and third leg signal I am giving to the second leg. So what will be effect on this? Hello, am I audible? Hello, hello, am I audible?
Yes, sir.
Yes, now we are changing the switching signal of one leg with other leg, exchanging the switching signal of one leg with other leg. Then what will be effect on the output voltage? Or which parameter will be changed of the output voltage? Which parameter of output voltage will change? If we just change the switching signals, interchange the switching signals of two legs, it means that we interchange the points B and C. Is it right? We interchange the points B and C, and from this we can say that which parameter can we change the voltage? Can we change the frequency? Or can we change the phase sequence? Which out of which three, if I change the switching signals of these two legs, which parameter I can change? Output voltage, output
Phase sequence, sir.
frequency, or the phase sequence?
Phase sequence.
Okay, correct. So we change the phase sequence. If you want to change the phase sequence, it is not necessary to physically change the connections of the load with the inverter. Only thing is that inverter control will automatically change the switching signal of the devices. Two leg switching signals will be interchanged, and we can control the frequency. Sorry, we control the phase sequence. Now, how to control the output voltage here? Any idea? Suppose I want to control the magnitude of output voltage. How should I change it? What option is available if you want to change the magnitude of the output voltage? Suppose I want to change the magnitude of I want to reduce the magnitude of output voltage. I will just draw to reduce the magnitude, or I use a pen here. Okay. Now I want to reduce the magnitude of voltage to a lower value. Okay, so drawing is okay. This will be, now I reduce the DC voltage here. So okay, this, now the output voltage magnitude will be definitely less. How to obtain that? What is the option available to control the output voltage? Anybody? How to control the output voltage? We have shown the red waveform. Okay, and that is definitely our output voltage is less as compared to whatever black waveform. So how to control the output voltage of the inverter in this case? How we control the output voltage of the inverter in this case? I have shown it here. Is it right? The red waveform. We have to change the VDC. So what option is available? Option available is we have to change the magnitude of supply voltage. Okay, we want to change this. We want to vary this magnitude. Okay, we want to vary this magnitude. So output voltage is controlled by controlling the DC input voltage. How we change? Now, how we change the frequency? Anybody? How we change the frequency in this case? How we change the frequency? Hello, am I audible?
Controlling the switching time.
Switching time. So here, if you see it here, so this T period, if you see here, we are having this T period. This T period, I can change it. Okay, this T period, I can make a small, frequency will be higher. If I made a T period higher, pattern will be remain same. Only the time can be expanded or compressed. T period, the pattern will remain same, whether we can expand it or contract it based on that. So by changing the T time, by the switching signal, we can control the frequency. So we have discussed how to control phase sequence. We discuss how to control output voltage, and third, we discuss how to control the frequency. Is it clear? So we control three parameters of this inverter. What are these three parameters? We control output voltage. How we control output voltage? By controlling the DC link voltage. Can it possible to change the wave shape with frequency? No, our wave shape is remaining fixed. Each device is conducting for 180 degrees, so wave shape is not changing. Only thing is that we have to change the amplitude of that wave shape, and this can be done by controlling the DC link voltage. So output voltage is controlled by controlling DC link voltage. Phase sequence is controlled by exchanging the switching signals of two legs. And how we control frequency? Frequency is controlled by controlling the TP rate. So is it clear? Is it clear how we control the three parameters of the inverter? Hello? Response is required?
Yes, sir.
Yes, sir.
Yes. Is it clear? Now let us, now if this particular, we have shown it here, again a line voltage, and we are having a phase voltage also, you can make it from line voltage. Okay, or we can go for a resistive load network and find out. So here if you see the below waveform, so upper whatever we discussed is the line voltage, and below waveform is the phase voltage. So what is the phase shift between line voltage and phase voltage? Anybody can tell? For a three-phase system, what is the phase shift between line voltage and phase voltage? VAN and VAB. What is the phase shift between VAB and VAN? Is there in phase, or is there a phase shift of 30 degrees? Who is leading? Hello, what is the phase
Line
shift?
voltage leads by 30 degrees.
Line voltage is leading the phase voltage by an angle of 30 degrees, and this is we have shown fundamental component trace out here, and fundamental component line voltage trace out here. Line voltage is leading by an angle of 30 degrees, and we are knowing line voltage will be a root 3 times of the phase voltage. Same is valid here. And now here we have shown the current waveform. Okay, if you see the current waveform, we have connected, let us assume the induction motor is connected. So what type of current it takes? It will not take a sinusoidal current. It will take a this non-sinusoidal current, because our voltage itself is a non-sinusoidal. We are already done the exercise of finding out the THD for this waveform. Can you recall? We have done the exercise for finding out the THD of this waveform. Yes or no? We have done this exercise of finding out the THD of the line voltage. Yes or no? Is
Yes,
it we
sir.
have done the exercise of finding out the THD of this waveform? Yes or no? Can
Yes,
you
sir.
recall?
Yes, sir.
Yes, we have done. This waveform is similar to our diode bridge source current. And what is our THD content this particular waveform? Can you just point out figure THD of this waveform?
31.92%.
31% around. Okay, so that we are already done it. And now here we have shown it here. We want to find out the, so with the help of this, okay, whatever our analysis earlier, that is we are having the expression of particularly AN. From that you find out fundamental component, and for this particular voltage you can find the square mean root. So RMS value of this RMS line voltage will be square root of 2 by 3 VDC. That will 0.816 VDC. And we are doing already V expression for AN. Already we have done the expression for AN. If you just go for this expression for AN, so this is our expression particularly, and this we have shown it here. A fundamental component of this will be root 6 by pi. It is for current. Now in this case we are having a line voltage in terms of the voltage. So our fundamental voltage is root 6 by pi VDC. But RMS value of a fundamental component is 0.78, whereas RMS line voltage is 0.816 VDC. And this will be, we are seeing already, we discussed how we control the output voltage. So one thing is we are controlling the output voltage by controlling the output voltage is controlled by controlling the input voltage DC voltage applied to the inverter. Okay, this will be one we discuss. And switching signal will not control the output voltage. Switching signal will control only the output frequency. And how to control output frequency? And output frequency is controlling by the T period of the switching signal. And we have seen that by interchanging the two legs, switching signal of two legs, we can control the phase sequence also. So now if you want to have a variable voltage and variable frequency, so we require a variable DC voltage at the input side. We require a variable DC voltage at the input. This is our 180 degrees mode of conduction. We just shown the symbol of inverter here constituting 6 devices. If variable DC, how we obtain? Another option is this variable DC we can obtain with a thyristorize converter. We obtain with a thyristorize converter, a 6 pulse converter, and this is LC filter we can get. And how we are getting the variable DC? Here we control the alpha, and for lower voltage alpha is more and our PF will decrease. So here we are already discussed the drawbacks of this particular thyristorize converters. Now let us go for another mode, that will be our 120 degrees mode of conduction. What is mean by 120 degrees mode of conduction? Each device conducts for a period of 120 degrees. So here our S1 is conducting for a period of 120 degrees. What is phase shift between S1 and S4? A phase shift between S1 and S4 is 180 degrees. So it is not like earlier case, okay, because they are 180 degrees phase shifted, signal is 180. Here our device is on for, S1 is on for 120 degrees. Then after 180 degrees of this, S4 will on. So a 60 degrees time, if you see it here, this is the 60 degree time where leg S1, leg 1, no device will be on here. S1 is on here, S4 is on here, but in this period or this particular period, we have shown that our no devices are on. So here phase shift between S1 and S4 is 180 degrees. What is phase shift between S1 and S3? Leg 1, phase shift between leg 1 and leg 2. The phase shift between first leg and second leg is how much? A phase shift between first leg and second leg is 120 degrees. Here we have drawn the lines of, if you see the vertical lines, we have made it of 60 degrees. So that S1 is on for 120 degrees. Then after that, S1 is off for 240 degrees and then on for 120 degrees. A phase shift between S1 and S3 is 120 degrees. So S3 will be on and then S5 will be on. So here in this case, what is the difference? In each leg, one device will be on in earlier 180 degrees mode up, but here out of these three, one will be on, and out of these three, one will be on. Okay, and so that here how many devices will be simultaneously on? Here only two devices will be on simultaneously. We don't require a date time. We don't require the date time. Same logic we can use for this. Okay, and then we can find out the output voltage waveform. So here, if you see here, each device conducts for a period of 120 degrees. Only two devices will be on from this. Out of 6, 2 will be on simultaneously. We are knowing the devices named S1, S2, S3, S4, S5, S6 as per conducting time, as per the conducting sequence. Here dead time is not required because after S1 is turned off, 60 degrees, no, S4 is on after 60 degrees. So we don't require a dead time, and the phase shift between the legs is 120 degrees. Now here we can find out the first phase voltages we can find out. So here we can find out the VAN, VBN and the VCN. So phase shift waveform, if you just put it here, let us go for one case how we find out the voltage. So let us go for first case AN, which devices will be on here. So we can get 6 and 1 is on. Let us assume that our devices here 6 and 1 is on. Let us assume that device 6 is on and 1 is on. This 6 is on means now B is connected to negative. So our B point we have connected to a negative, and 1 is on means A is connected to positive. So here this is on and this is on. First 60 degrees we have 6 and 1 is on. Is A is connected to positive. This is plus, A is connected to positive and B is connected to negative. Then what will be happen? So this 3, okay, you see that C is not connected anywhere. Here, if you look at this case, our C is not connected to anywhere. And these 3 resistances are equal. three resistances are equal. So here whatever VAN and VBN, okay, VBN. So VAN will be this is a total across AB, that is AB is a VDC, total voltage. Resistances are equal with respect to N. So if the voltage will be divided equally, so VAN will be a plus VDC by 2. VAN, so here if you see it, VN is plus VDC by 2. Whereas VBN is with respect to B is negative with respect, and so this VBN is a minus. And what about the VCN? VCN is not connected, so VCN voltage is 0. So here we have shown it here, this case, whenever device 6 and 1 are conducting, then AN will be a plus VDC by 2. Then BN will be a minus VDC by 2, whereas CN will be 0. Which will be next devices will be on. Next devices on will be now 6 and 1. Then each device is on for a period of 180. So it will be, sorry, 120, 1 and 2. Here devices conducting will be 1 and 2. So here devices conducting 1 and 2. So it means that our 1 is on, means A is connected to positive. 2 is on. Now 2 is on. If you just see, now we are having a 2 is on, sorry. So 2 is on, 2 is on means this is on, means our C is connected to negative. C is connected to negative. So BN will be 0 here because B is not connected. So BN will be 0 here. Okay. BN will be 0 and AN will be a plus. Whatever we are having, this is a plus VDC by 2. And now CN will be a minus VDC by 2. So you just go on like this and we are getting the VAN, VPN and VCN. We get a 3 phase voltages where we are having, we created a star connected load and the neutral point here. This will be N of this particular star point here. And then we get this phase voltages. And so phase voltage is a cos square wave. Okay, where their line voltage is in 180, line voltage is cos square wave. That is the difference. And now once we are knowing VAN and VBN, we just copied here. And how we get the VAB? What is our VAB? VAB will be equal to VAN minus VBN. VAB will be equal to VAN minus VBN. So BN minus BN means, so you invert it and add it. Okay, so invert it, add it. This is a minus VDC particularly for this case. If you invert it plus VDC by 2, VDC by 2, so this will become out to be a VDC. Next here it is 0, so remaining will be a plus VDC. Here this is a positive, okay, VDC by 2, so it is VDC by 2. Here inverted minus, this we have to make it minus, so this minus minus again minus VDC. So you just use the expression VAB will be equal to VAN minus VBN. So we are knowing the VAN waveform. This is our VAN waveform. You invert the VBN and add with VAN to get the VAB. So this is our VAB waveform. Step particularly this. So you just remember this lower voltage waveform is the line voltage waveform. So wave steps are just interchange, magnitudes are different in case of 120 and 180 degrees. Here also how we control the output voltage. How we control the output voltage in case of 120 degrees mode of conduction. How we control the output voltage. I want to control the output voltage, means I want to, option available is only I have to control the DC magnitude. Is it right? So how we control output voltage in case of 120 degrees mode of conduction? How we control output voltage? Anybody?
Changing VDC.
Changing VDC is the only option because switching time of devices are fixed. Okay, each device is conducting for a period of 120 degrees, and that is why only option available is to control the input voltage. And we can change the frequency by controlling the T period, whatever we have done for 180 degrees. Similarly, we have to done for this. So we have to change the T period. So this is our T period. Okay, so we can increase it or decrease it. This is our T period. Okay, and with the help of this, so this is our T period. By changing the T period, we can control the frequency of this. And now third is how to change the phase sequence. How we change the phase sequence? Same as whatever done in case of 180 degrees mode, we interchange the switching signals of the two legs. But here what happens if you find out our output voltage is less because devices are conducting for 120 degrees. So if you find out RMS value of this line and phase voltage and corresponding the RMS and line voltage, RMS voltage of line and phase, then we have seen that 120 degrees mode of conduction will be giving the less voltage as compared to the square wave inverter or as compared to 180 degrees mode of conduction. So you just calculate this. Now next we are going for, that is very important, is we are going for a PWM technique. So 180 degrees and 120 degrees mode of conductions normally not used. In case of CSI we are using 120 degrees mode of conduction, whereas 180 degrees mode we are normally not using. There's having drawbacks because THD of the voltage is around 31%. So instead of that, we are using the various PWM technique, pulse width modulation techniques. So for three-phase bridge inverter, we are having various PWM techniques. Okay, and we are just listed here various PWM techniques. So one is sinusoidal PWM that you have studied in power electronics. Sinusoidal pulse width modulation. In short, we are calling as sinusoidal SPWM. We are calling. Then another is selective harmonic elimination PWM. A specific harmonics we can eliminate. We want to eliminate fifth and seventh in case of bridge. That is also possible. So a specific harmonics we can eliminate. That technique is available. That we can call as selective harmonic elimination PWM. Then another we are having a space vector PWM. Okay, space vector PWM that we are going to discuss afterwards. Then hysteresis band current control PWM, sinusoidal PWM with instantaneous current control. So out of that, and now today we are going to discuss very first PWM technique. Okay, remaining techniques will come with at different times, but now today we want to discuss about the sinusoidal PWM technique. So this is how we generate. This diagram particularly indicate how we generate the switching signal for the 6 switches. Okay, so we are already knowing a leg 1 is having the switches S1 and S4. Okay, second leg we are having S3 and S6, and third leg we are having S5 and S4. So how many switching signal we have to generate for the inverter? We have to generate the 6 switching signals. And here we are comparing the two waves. Here we are comparing the two waves. For generating this signal, we are comparing the two waves. So which two waves we are comparing? One is modulating wave, and that is nothing but a sinusoidal. This modulating wave, sinusoidal wave, modulating wave we can call is a sinusoidal in nature. So one is we are in 3 modulating waves or 3 sinusoidal waves having a phase shift of 120 degrees. So this V1, V2 and V3. V1, V2, V3, these are 3 sinusoidal modulating waves. That AM sine omega t, peak amplitude of that modulating wave, AM we are calling. Then AM sine of omega t minus 120, AM sine of omega t plus 120. So this modulating wave has a frequency equal to omega. It is having a frequency equal to omega radians per second. It is having a frequency, and this wave has having an amplitude. Peak amplitude will be equal to AM. Peak amplitude will be equal to AM. So is it clear? So we are required 3 modulating waves which are sinusoidal in nature, and of that we can control omega as well as amplitude. So here, this particular in three modulating waves, we can control the AM. AM can be also varied. Also the omega can be varied. Okay. So here we have seen that for these three particular modulating waves, we are controlling the amplitude as well as the frequency. Omega we are controlling as well as amplitude we are controlling. And but the phase shift between these three modulating waves is 120 degrees. Each we are having the same amplitude, same frequency. Okay, so all we are having the same amplitude and same frequency simultaneously. All these three waves we can control the amplitude as well as a frequency, or a modulating wave frequency we can control. So this is about our modulating wave. Another wave we can call as a carrier wave. So for this we require only one carrier wave. Carrier wave is our triangular wave. Okay, it will be a triangular wave, and it is having a fixed amplitude and fixed frequency. So this carrier wave is having a fixed amplitude and fixed frequency. We are not changing the frequency of this carrier wave, and its amplitude also remains fixed. Whereas for modulating wave, we are it is possible to control the amplitude as well as the frequency, whereas here we are not controlling the frequency and amplitude of the triangular wave, and that is fixed. And this triangular wave we are calling it as a carrier wave. Look at the diagram here. If you looking at this diagram, you see that we are having these are three modulating waves, V1, V2, V3. They are giving to a non-inverting terminal of op amp. This is the symbol of op amp, you can call it. We are comparing these two signals. Three modulating wave are compared with a one carrier wave. Carrier wave is having a fixed amplitude. Its AC is fixed, its amplitude is fixed, and its frequency is fixed. So carrier wave is fixed. It is one for all this. So carrier wave is given to a inverting terminal of these three op amps, and V1 is giving here for op amp number one, V2 is giving to a second, and this. And the comparison result directly is the switching signal for S1. V1 with carrier wave. V1 modulating wave with the carrier wave comparison signal will be a +1 and -1, you can call it, or 1 and 0. That signal will be directly going to a switching signal of device number 1, and inverted switching signal will be going to a device number 4. Then a second comparison is made between a carrier wave and second modulating wave, and this direct comparison signal will go to S3, and inverted of that will go for S6, lower devices of the second leg. And this is our V3, a third modulating signal is compared with again the same carrier wave, and comparison results will be going for S5 and S2. So here we generate the switching signals. We are calling as sinusoidal PWM because we are using a sinusoidal modulating wave, okay, for generating the switching signals. And we generate the switching signal by comparing two waves. One is modulating wave of its frequency as well as amplitude is variable, whereas it is compared with a carrier wave, a triangular wave with fixed frequency and a constant amplitude. Its frequency is fixed and amplitude is fixed. Now let us we can just go for one how we generate the switching signal. So here we have shown it here, a carrier wave, that is a triangular wave. If you see it here, we are having a triangular wave is compared with a modulating wave, is compared with a modulating wave. And here when modulating wave is higher, what is our logic? So we can just put the logic here. So let us Vm, we can call it. Vm is greater than V carrier. What will be our output? Output will be a +1. Okay, it is a +1. Output is a +1. So here modulating wave, we see it here, modulating wave is higher as compared to carrier wave. Here carrier wave, if you see it here, this carrier wave is lower than the modulating wave. When Vm is greater than Vc, our output will be a plus 1. And when Vm, modulating wave, is less than Vc, we can say that output will be a 0. We can call it 0, or we can have a minus 1, whatever you can say. Minus 1 can be converted into 0. So here Vm is less than Vc. So here if you see it here, this period, if you see it here, our modulating wave is less, whereas carrier wave is more, and in that case, we have shown it here. This will be a 0. Whereas here, our carrier wave, modulating wave is higher, we can have a plus. So here we generate a comparison results. This is for compare when Vm is greater than Vc, that is Vm modulating wave amplitude is greater than Vc, our output is plus 1. And when Vm is less than Vc, output will be 0. So this is a comparison result. We can apply a switching signal for S1. This is the switching signal for S1. So whatever this we obtain, the switching signal for S1 here. So this will be comparing this modulating wave, carrier wave with modulating wave. And when Vm is greater than Vc, if you see it here, Vm is greater than Vc, our output voltage of S1 is positive 1. Where if you see it here, more period you have seen that our modulating wave is less than Vc, the output will be a 0. So this is a switching signal we can obtain for a device S1. Then how to get the switching signal for S4? And switching signal for S4 is just invert the signal of S1. So switching signal, we just inverted it. So this will be a switching signal. You can say it is for S1 and S4. How will be switching signal for S3 and S6? It is same, but our carrier wave will be modulating wave will be phase shifted by 120 degrees. So here we have shown it all three modulating waves here. So V1, if you see it here. So if you use a V1, comparison of this V1, we use device number S1 and S4. With the help of that comparison of this V1 with carrier wave, we get a switching signal for switch S1 and S4. If you make a comparison of V2, then we get a switching signal for S3 and S6. Okay, and then if you are having a V3 is compared with our carrier wave, then we get a switching signal for a 5 and 2. Okay, and we have shown it here. This is how we are generating the switching signal. Logic will be remain same. Whatever we have discussed here, we compare this. Carrier wave is one here, which is having a fixed amplitude and fixed frequency, whereas the sine wave signal, that can be its magnitude can be reduced. We can reduce the magnitude here as like this. All these we can reduce it, or we can change the frequency also. So we reduce the magnitude as well as frequency, and with the help of that, we are generating the 6 switching signals are generated. And now based on that, here we have shown it here how we get the VAO. Here we made a center point of DC that we can call as O. Okay, and this is a point A. When upper switch is on, S1 is on, what is VAO? When S1 is on, VAO will be plus VDC by 2. So here it will be a plus VDC by 2 when we are our S1 is on. And when S4 is on, it is a minus VDC by 2. So this will be how we get the switching signal of VAO and this. Okay, so VAO is nothing but a center point of DC with A. And here what is our logic? When S1 is on, VAO is plus 0.5 VDC. And when S4 is on, VAO is minus 0.5 VDC. With that, we can get the VAO signals. And this particularly, we can get now how we get the output voltage waveform, line voltage waveform. For that, let us look at this diagram. We created one point that we can call as a fictitious neutral. This is not the neutral. You can call as an end point. If you see it here, this is an end point. With respect to that, we are getting the voltage AN. We get the voltage AN here. VAN. This N is not our neutral point. It is a common negative DC link point. What should be a magnitude of VAN? What should be a magnitude of VAN? Anybody? When S1 is on, what should be magnitude of VAN? Suppose S1 is on. S1 is on. What is the magnitude of VAN? S1 is on. So A point will be connected to plus VDC. This A point is connected to, as S1 is on, A point is connected to plus VDC. So VAN will be equal to plus VDC when S1 is on, particularly for S1 is on. What is VAN when S4 is on? Anybody? What is VAN when S4 is on? Anybody can tell what is value
Zero.
of VAN? It will be
Zero.
0. 0 when
Yes, four.
S4 is on. Okay. So here, when S4 is on 0 and when S1 is on plus VDC. So this is our AN. AN nothing but our, when S1 on, it is positive value, because here we are using this. When S1 on, it will be a plus VDC. When S4 on, it will be a 0. So for this we are getting the switching signal of S1 and S4, and based on that we can get this output voltage waveform VAN. What about VBN? When S3 is on, VBN will be plus VDC, and when S6 is on, VBN will be a 0. So this is the second waveform. We get a VBN. Okay, VAN is known, and this is the VBN. And now here N is common. Now how we get VAB? Here VAB is VAN minus VBN. Here we get a VAB. Here we get a VAB. VAB will be, how we get? VAB will be equal to VAN minus VBN. VAN will be equal to minus VAB will be VAN minus VBN. So this will be a plus. You just invert it and take the difference between this, and this will be our output voltage waveform. So third is our PWM output voltage, a line voltage waveform. Okay, this will be a line. Any question on this? Any doubt? How we find out the line voltage VAB? How we obtain the line voltage VAB waveform? For that, at the DC link, negative of the DC link, this is a negative part of DC link, we have created a 1 point N, and we get the AN. Logic is S1 on, AN will be plus VDC, then S4 on, VN will be 0. Similarly for BN, S3 is on, BN will be a plus VDC, S6 is on, VBN will be a 0. And this, with the respect to switching signal, we draw the VAN waveform and the VBN waveform. So we get the VAN waveform and the VBN waveform, and based on that VN minus BN, this is our line voltage waveform. This will be our, it is having a, this magnitude is plus VDC minus VDC. So we are having a switches, a width of the pulses, yes, it may be varying sinusoidally. Width of pulses is varying sinusoidally, and that is why at 90 degrees, if you see it here at 90 degrees, our width of pulse is maximum. So width of pulse is varying sinusoidally, and that's why it is called as a sinusoidal PWM. Okay, so today we stop here. If you are having any questions, so today we discuss 180 degrees mode of conduction, then 120 and a sinusoidal PWM. And here for controlling output voltage and frequency, we want to control the output voltage and frequency. So output voltage is controlled by controlling AM. So how we control? Output voltage is controlled by controlling the magnitude of AM. A sinusoidal Modulating wave peak amplitude we can control. With the help of that, we can control the output voltage. How we control the frequency? Output frequency is same as modulating wave frequency. If you go here, we see it here, the output frequency. If you see it here, output frequency will be the same as that of modulating wave frequency. So we control the modulating wave frequency to control the output frequency. So AM is controlled to control the output voltage, and omega is controlled to control the output frequency. And how to control phase sequence? Just interchange the switching signals of two legs. Just interchange the switching signals of the two legs. So we are having some time. Any doubts regarding this? How we generate the sinusoidal PWM, and how we control the output voltage, output frequency, and phase sequence in all three cases, 180, 120, and sinusoidal PWM, how we control output voltage, how we control frequency, and how we control the phase sequence. So any question? Any question?
No, sir.
Okay, so when will be our next lecture? Okay, let us timetable maybe change, we see, otherwise we will meet on Wednesday, or if possible there is change, as per the new change we can meet in the next week. Okay, thank you.